Okay, the next talk is SETH-Hardness of Coding Problems by Noah Stephens-Davidowitz and Vinod Vaikuntanathan. And Noah will give the talk.
Thanks. So every time I go to a conference or every time I speak at a conference, I check whether or not my last name is the longest last name of any author in the conference. The answer is yes. It's always yes. This time I thought I might have a shot at having the two longest last names in the conference on a single paper, but it turns out that the distribution is sort of exponential. So Vinod's name's a little shorter than mine, and there are many, many people, perhaps some in the audience, who beat Vinod. Okay, so that's what's important. Let's move on to the talk. So I'll be telling you about SETH-Hardness of coding problems. Okay. So first, I'll define codes and the coding problem that I'll mostly talk about. So a linear code comes with sort of a lot of fancy vocabulary and notation. So I'm going to call 0, 1 the field with two elements. I'm going to denote it f sub 2. It's just bits. And I'm going to call 0, 1 to the m, so bit strings, a vector space over the field with two elements. And since this is the session on codes, I imagine you all know this, but I'm just hoping you get used to my notation. A subspace of this space is the column span of some matrix, C, m by m matrix, and I'll write it like this. Then a linear code is just a subspace. And so in other words, it's the column span of some matrix, and I'm going to say that n is the rank of this code, and m is the ambient dimension. And for some reason, we call elements in this subspace code words. And then when things get really fun is when we add this sort of Hamming norm to our space. So now we sort of add geometry to it. So we count the number of ones in this string. We call it the Hamming norm, and suddenly things get quite interesting. In particular, we can ask fun computational questions about these objects. So the main thing I'll be talking about today is called the nearest codeword problem. It's a computational problem. You have as input this generator matrix C, and then some other vector T. And we can define the distance between the target vector T and the code as just the minimal distance between T and any code word. And NCP, the nearest codeword problem, asks us to compute this distance. And this is a very, very natural problem, right? Another way to view it is I'm given a system of linear equations over F2, and my goal is to satisfy as many of them as possible. So I would call this maybe max XOR sat. This is equivalent to NCP just by sort of squinting. So what do we know about this problem? Well, there exists a 2 to the n time algorithm, ignoring polynomials, I guess. There also exist highly non-trivial and really quite beautiful algorithms in the regime when the ambient dimension is not much larger than the rank. In particular, there's this amazing 2 to the m over 20 algorithm by Becker, Zhu, May, and Maurer. But for large M, we don't know anything non-trivial. There do exist approximation algorithms. Of course, this is a kind of classical NP-hard problem. We've known that it's NP-hard since the late 70s, and a sequence of work showed that it was hard to approximate. But we didn't know any fine-grained hardness. What I mean by this is that NP-hardness results say there's no polynomial time algorithm. And maybe if you sort of open up the black box of the reduction, you can say, look, there's no algorithm that runs in 2 to the n to the 10 time, 2 to the n to the 1 over 10 time, or something like this. But it doesn't rule out the potential that there could be much, much faster algorithms than the ones that we know, 2 to the square root n, or 2 to the n over 100, or something like this. What we do in this work is we show that there's no non-trivial algorithm for the nearest codeword problem under this strong ETH assumption, which I'll show you. So in other words, the fastest algorithm runs in 2 to the n time up to smaller order terms under a complexity theoretic conjecture. And I'll just sort of mention, I came to this from a funny angle. I was originally, my co-author and I were originally motivated from cryptography and from lattice problems, but you don't need to know anything about that for this talk. Okay, so let me explain how we prove the SETH-Hardness of NCP. And one thing that's fun about giving this particular talk is that the proof is quite simple, so I will show you the entire proof, which it might sound scary, but it's not. Okay, so first I will define the strong exponential time hypothesis. So it's defined in terms of KSAT. So KSAT is a problem that I imagine you're all familiar with. You're given a KCNF, so that's a bunch of n's of the ors of k literals. And just some notation, n will be the number of variables, m the number of clauses. And the celebrated strong exponential time hypothesis, which was introduced by Impagliazzo and Pittori, says that, well, it's a little more fancy than this, but my version is there exists a constant integer k such that there's no 2 to the 0.99n time algorithm for KSAT. The formal conjecture, there's an epsilon as well, and k depends on epsilon. So what do we want to do? We want to show that there's a reduction from a KSAT instance with n variables to an NCP instance with rank n. If I could do that, then that would imply that if SETH is true, then there can't be a 2 to the 0.99n time algorithm for the nearest Codeword problems, and no non-trivial algorithms. So this is what I mean when I say that we've proven this. I mean we've shown such a reduction. Okay. So what's our reduction going to look like? Well, okay, I need to come up with some generator matrix C and some target vector T. And the generator matrix has to have n columns by definition, right? I need it to have rank n, so it has n columns. And I have n variables, so I'm going to make each column correspond to a variable. So my first column corresponds to x1, et cetera. And I want this code to have the property that the distance between CZ and T should correspond to the number of satisfied or unsatisfied clauses satisfied by Z, right? So here Z is a 0, 1 vector. I'll view it as an assignment. Does this make sense? So let's first show a reduction from the 2-SAT problem without negations. You might realize that this is not an NP-hard problem. It's in fact trivial, but somehow it shows most of the ideas. So let's say just we have the clause x1 or xn. And I sort of want my row here, my top row, to correspond to this clause in some way. And I'm just going to tell you that the target vector is the all ones vector. I think you'll see why in a second. So let's just imagine what we can do here. So presumably, since x1 and xn are the only elements in my clause, probably only the first and last column will have non-zero entries. So I'm just going to ignore everything but the first and last column, and therefore I'm going to ignore everything but the first and last coordinate of my z vector. So I'm going to look at z1 and zn, which you can think of as assignments to x1 and xn. And I can just imagine what I'll put in the sort of 2 spots of my row that are undetermined. Maybe I'll put 1, 1. There aren't that many choices. Let's try this one. So if I put that one, it won't surprise you to realize that this actually doesn't give me what I want, in the sense that now the first coordinate of c times z, well, it'll be 1 if z1 doesn't equal zn, and 0 if z1 equals zn, which is not what I want. What I want is for it to be 1 if z1, zn satisfies x1 or xn, and 0 otherwise. Right? And this does not work because if z1 and zn are both 1, then this gives me a 0 when I would like there to be a 1. So I don't know. There are only 4 possibilities. Let's try some more. We can try this one as well. So 0, then 1. And of course, this just gives us zn back. So this, again, is no good because there's a satisfying assignment given by 1, 0 that is not captured by this. OK, not too many more to go. If I do this one, now my function is z1. And again, there's a satisfying assignment not captured by this. It's the assignment that sets zn to 1 and z1 to 0. So nothing worked. I guess I can also try 0, 0, but that's particularly silly. But what works is doing all of them. So if instead of doing just having one row per clause. I have many rows per clause, and I just sort of write down every binary vector. Here I've left out 0, 0 because it's kind of silly. Then if you stare at this for a second, you'll realize that the first 3 entries in C times Z will contain 2 1s if and only if the clause is satisfied by Z. Otherwise, I guess it contains 0 1s because it's 0. OK. So that was for 2sat. Let's do ksat now. It turns out generalizing, it's really not so hard. So I'm just going to write down what's called the Hadamard matrix with k columns, which is just the matrix consisting of every possible row I can write down. So if you like the row 0 is 0 in binary, row 1 is 1 in binary, row 2 to the k minus 1 is 2 to the k minus 1 in binary. And still, my target is going to be the all ones vector. And this has this really rather nice property. In fact, it's unique in having this property, that the Hamming weight of hz XORed with t is large. It's 2 to the k if z equals 0, and it's 2 to the k minus 1 if z does not equal 0. Right? And this is just sort of the fact that if I take a random parity of a non-zero vector, it'll have parity 1 with probability 1/2. And of course, the 0 vector always has parity 0, no matter what I take its inner product with. Good. So we're almost done. Let's finish the reduction without negations. Still not reducing from a hard problem, but we're getting there. So say I have some gigantic clause, x1 or x3, all the way up to xn. What I'll do is I'll just put the first column of my Hadamard matrix in the column corresponding to the first variable, x1, the second column in the column corresponding to the second variable, x3, et cetera. And I'll just fill up this matrix like this. Then I'll do it for another clause and for another clause, et cetera. In general, I put the ith column of hk in the column corresponding to the ith variable in the clause. And everything else is just 0. And then you stare for a few more seconds, and you realize that this has this very nice property, that the distance between cz and t is going to be 2 to the k times the number of unsatisfied clauses plus 2 to the k minus 1 times the number of satisfied clauses. So in particular, the distance tells me exactly how many clauses are satisfied, and the minimum distance out of all z tells me the maximal number of clauses that are satisfied. So if you like, this is even a reduction from max ksat with no negations. OK, so one last thing to do. Let's worry about what about if I have a negated variable, a negated literal. So all I need to use here is a simple linearity trick, right? So I notice that if I shift my target by hk times z prime, and then I use linearity, and I remember the original property that I had, then I get this same sort of cases, but now I'm at distance 2 to the k if z equals z prime, and 2 to the k minus 1 when z does not equal z prime. So this is sort of just a slight twist on what we already had. And then you just sort of have to think about what a ksat clause actually is. A ksat clause actually is just a description of assignment to k variables that are not accepted, right? People don't often describe it this way, but this is a perfectly reasonable way to view it. For example, if it has no negations, then the all zero string is banned and everything else is kosher. If I want to ban z prime, I'll just use the gadget. I'll use the target corresponding to z prime. So maybe just show one example. If my clause looks like this, x1 not x7 xn, then my target vector, I'll take my original target vector t, which was just the all ones vector anyway, and I'll just add to it hk times 0, 1, 0, or 0, 1, 0 is just like the pattern of negations in this clause. So nothing fancy. And then this is sort of the part of the talk where I point out that we just proved the main result. It really wasn't very hard. In particular, we still have this property that the distance between the target and the code corresponds exactly to the maximal number of satisfiable clauses, and therefore, if SETH holds, there's no 2 to the 0.99n time algorithm for NCP. So I told you it wouldn't be that bad. I think it wasn't that bad. And I'll just say that, again, the way that we came to this was quite strange. We have a semantically very, very similar reduction in the world of lattices in joint work with Bennett and Golovnev, and then Agarwal, Bennett, and Golovnev. That's much, much, much more difficult. And somehow we found this second, which is really kind of strange. And our hope was to understand this better, to understand that better, but somehow it's too simple to understand. OK, so we proved some additional results. First of all, you might have noticed that the matrix I constructed is sparse in the sense that each column has each row has at most k elements, k non-zero elements in it. And what this means is you can view this as like an instance of what I would call max k XOR SAT, or max k 2 lin. So in other words, if I'm given many linear equations on each of one only has k variables in it, then I actually reduce to that problem instead, and the proof is the same reduction. We also show 2 to the n hardness of constant factor approximation under the assumption that you have a similar hardness result for KSAT. In fact, this is quite recently conjectured by Manu Rangzi in his thesis. It's a very elegant hypothesis. I won't present it. And again, the proof is the same reduction. Our reduction preserves approximation factor, or doesn't preserve approximation factors, but maps constant to constant. We also show 2 to the n hardness of the nearest Codeword problem with preprocessing. So this is the variant of the problem in which you're allowed to play with the code for as long as you want, and then you're given the target, and you have 2 to the n time to solve it. We show that there's no non-trivial algorithm for this as well, and the proof for that is a slightly different reduction. And finally, we extend this to Q-array codes. I could have shown you the proof for Q-array codes more or less just as easily. I just would have had to define a Q-array code. But in particular, we show that it's Q to the n hard to solve NCP, or even the problem with preprocessing, under the SETH assumption. And the proof, again, is a slightly different reduction. Actually, the hard part of the proof is playing in the SAT world. We have to show that there's a Q-array analog of SETH. We do show that. And this is a slight improvement on work of Traxler. Traxler somehow wasn't interested in as tight constants as we wanted, so we improved upon him, but I'm sure he could have done it if he'd wanted to. Finally, I'll just sort of say what the minimum distance problem is, and the fact that we also prove the same result for the minimum distance problem. So the minimum distance problem is the homogeneous version of the nearest Codeword problem, in the sense that I want to know now the minimal Hamming norm of a non-zero element in the code. And it's known to be no harder than NCP, and it seems to be kind of morally much easier. The algorithmic status is roughly the same. The way in which it seems to be easier is that it's a lot harder to prove hardness. In particular, it took us 19 years to go from proving hardness of NCP to proving hardness of MDP, which was proven by Vardy. It's a really extremely beautiful proof. And there's been a sequence of work showing hardness or approximation. There's been a lot of interest in this. We show that SETH rules out better than Q to the n time algorithms for MDP over FQ. So again, there are no non-trivial algorithms for this problem. And the most natural reduction is randomized. We actually, with the help of a reviewer who might be in the audience, we learned how to de-randomize this. So thank you, reviewer, if you're here. And we show hardness or approximation, not quite as strong as what we're able to show for the nearest Codeword problem. In particular, we need to use this very heavy hammer, and this costs us some gigantic constant in the exponent. But I'm running out of time, so I'll not say more about that. The very rough proof idea for the experts, we followed Dainur, Machancho, and Safra. So in summary, we showed there are no non-trivial algorithms for the two most important coding problems, assuming SETH. The same holds for even with preprocessing. For constant factor approximation, we get morally similar results. And that's essentially all I want to say, except for an extraordinarily shameless plug. I'm on the job market.
Questions?
Yeah. So good. So the hypothesis, it's not clear if this is the right hypothesis. I've talked to Payson, he agrees. The one that Payson wrote down is for every epsilon, there exists an approximation factor gamma and a k such that it is 2 to the 1 minus epsilon n hard to approximate ksat up to a factor gamma. Did that translate? Okay, so the difficulty in defining this is that as k gets larger, ksat becomes easier to approximate in the sense that it's trivial to approximate it up to like 1 minus 2 to the minus k or something like this, right? So the conjecture is that like as k gets larger, there still is always some constant factor approximation, and then you get like an SETH style thing where like as epsilon goes to 0, k goes to infinity. Yeah? And we prove that like a similar thing holds for NCP in the sense that as your running time approaches 2 to the n, or even q to the n, the approximation factor goes to 1, but constants map to constants. Is that? Yeah, it's a little complicated. Uh-huh.
Anything over the reals, like if I give you a matrix and ask for a linear dependence of size k?
If I give you a matrix, I see. So some versions of this problem are easy, right? Depending on the specific details. I guess the short answer is I haven't really thought about that much. Yeah.
Okay, let's thank the speaker again.